Okay, so we understand that conduction occurs when you have an electric field in a conductor. The electric field accelerates electrons in the direction opposite the field because electrons are negatively charged. Electrons interact with each other, but more with the ions, the atoms, from which, each atom in copper, for example, has lost an electron through the conduction line. So electron comes along and interacts with that positive ion, which tends to attract it and slow it down. But the electron's moving so fast that it doesn't actually join back into the atom. And it's in the conduction band, and there's all kinds of stuff about that that we're not going to have a chance to cover. In any case, that's where resistance comes from the fact that the electrons are moving really fast. You can do 3/2 kT at 300 Kelvin. Okay, at 300 Kelvin, 3/2 kT is about 10 to the negative 21st joules, 4 times 10 to the negative 21st. Electron has a mass of 10 to the negative 31st, negative 30th, 9.11 times 10 to the negative 31st, just about 10 to the negative 30th kilograms. Meaning that if you divide the energy by the mass, you're going to get 1/2 square v, 1/2 v squared. And 1/2 v squared is going to be in the order of like 10 to the 9th meters squared per second squared. So these things are moving at tens of thousands, over 10,000 meters per second, if my calculation is correct. Okay, it's many thousands of meters per second. The electrons, due to the thermal agitation, because the ions, the atoms, are vibrating. They interact with the atoms, and they pick up the energy, the vibrations, just equalization of energy. So the average electron has the same kinetic energy as that vibrating atom. The vibrating atom is tens of thousands more times more massive than the electron, so they pick up a whole lot of velocity. Okay. So as a result, the path of an electron, of course, your book has a picture, but electron. Okay, starts here, it goes away, it collides into something, comes back, it collides. Now, these should be sharp corners here. I'm a little clumsy today. Essentially at every collision, actually. Okay, that's a classical model. Really, the collisions are electrostatic, and if you got two things approaching each other, not quite head on, they come up here. If they repel, the collision is going to be kind of like this. They're going to curve away from each other because of the electrostatic repulsion. If they attract, they come back this way, and they tend to attract, and they tend to go like this. And that's what's really going on. But we can still model it with as if these things are hard balls colliding with each other. It comes out the same in the long run. So, it's like you got an electron here, and after several collisions, it's here. Why is it here instead of here? Well, that could just be random, a random walk, okay? Random collisions and so forth. But if there's an electric field, actually, electric field in this direction, okay, it's going to push the electron in that direction. So that in the process of all these random collisions, the electron is going to tend to migrate that way. That's how you get the slow drift of the electron cloud. All right, well, you can calculate the velocity of the electron cloud if you know how many electrons there are per unit volume, and you know the cross-section area of your conductor. It's a very simple calculation, so I'm not going to talk too much about that. Okay, I want to talk about conductivity. Now, Okay, E gives you this. And the collection of all the electrons drifting this way gives you. Okay. And J equals. Well, J is proportional to E. Okay, so P, rho is your proportionality constant. Called the conductivity, except rho should be resistivity. So what I did there was. And 1 over rho times it. So rho is. E over J. It's the ratio, the proportionality constant between electric field and current density. And of course, your current is your current density. Current density is in current per unit area. Multiply that by the area. And I'm going to put a CS on that. Cross-sectional area. ACS is constant. The current. Where I want to go, not where I am. Then your electric field is V over L. For conductor like that, if your cross-sectional area is constant, then E is V over L. I mean, that comes from what's voltage. Voltage is your work per unit of charge. Electric field is your force per unit of charge. You divide the work per unit of charge by the distance over which that work is done, which will be the length of your wire. You get the force per unit of charge. It just, I mean, you got this equation, you probably memorize V equals ED. Okay. Again, okay, use that equation, but this is saying the same thing. And what it's saying again is you get your work per unit of charge by multiplying your force per unit of charge by the distance over which that force is exerted. Okay. Okay, so you get E equals V over L. Okay, we can write this. Basically, current is this. equals voltage over resistance. Well, resistance is, well, here's your voltage and here's your resistance. And something about that bothers me, but that's right. It's not right. Something's gonna be in the denominator. Multiplied by ACS, right? So I put it in the denominator. And then I realized that made no sense. Makes no sense when I do this. Turns out it's this and the ACS. You multiply this by the cross-sectional area and think about why that is. Think about why that makes sense. Don't just use it as a formula. This is the current per unit of area or density, and that's the area. Multiply the current per unit of area by the area, you get the current. So then for this, well, we put it all together. You should really understand every bit of that intuitively and be able to interpret every bit of that. And we got a question because I probably did something ignorant, so something else ignorant. Yeah, I probably should have written this down before I did this. I got this upside down, the L and the A. Now, among other things, the units of rho are ohm meters. And L over A has units of reciprocal meters, meters over square meters. So the units work out. Okay, well, I had it, the units didn't work out at all. And the thing that alerted me, among other things, didn't look right. So what I had even before that was I was doing rho times volume. And that didn't make any sense at all. So you want to think about the sense of what you do and make sure you interpret it. If you tend to write things down wrong like I do, just carelessly, you go back and think, does that make sense? So what I had didn't make sense. Thank you for the correction. Okay, so anyhow, there's your definition. Again, you go back to what it means for a conductor to conduct electricity, to conduct current. What does current mean? It's the rate at which charge drifts past a cross section. Current density is just proportional to E. We're going to call this resistivity. This being a resistance, a large rho is going to interact with an electric, not interact. A large rho though is going to tell you that for given electric field, you don't get a lot of current. Smaller rho, you get a lot of current for given electric field. Okay. And then you say, okay, rho is E over J. Current, as we already know, is just density times cross-sectional area, and that's intuitive. Current per unit area times area. And then everything else develops accordingly. Okay. So rho is a number you can look up. Take your phone, your computer, look up a table of resistivities. Okay. But let's just calculate a resistivity. Let's say we've got and we're going to do a wire, and we'll make it a square. One millimeter square cross section. Just because it's easier to calculate the cross sectional area. You don't have to involve pi and r squared. Okay. Okay, ohms is the measure of resistance. And we'll relate that to other units. I mean, resistance is voltage over current. Okay. Voltage is work per unit of charge. Current is charge per second per unit of time. So you can get what the units of resistance would be in basic SI units, but right now we'll just say, okay, resistance is ohms. And if you divide voltage in volts by resistance in ohms, you get current in amps. So right now that's what an ohm is. So what's wrong? Okay, so it's a simple calculation. You got to be careful when you figure the area per square millimeter. Millimeter is thousandth of a meter. You square that, you get a millionth of a square meter. So it's 10 to the negative 6 square meters. And of course, you know, we solve this equation for rho, that's trivial. We got this. Okay. So we plug in our 10 to the negative 6 square meters, our 10 ohms, and our 2 meters, and then we get it. Okay. Now that is, I was trying to estimate what a thin piece of nichrome ought to do. And that's actually, I think, fairly close to the resistivity of nichrome. It isn't all that close, but it's in the right ballpark. Okay, now typical resistivities are about 1/100th of that, which would be a 10 to the negative 8. Okay. Resistivities of good conductors are in small single digit multiples of 10 to the negative 8 ohm meters. Okay, I think 2 times 10 to the negative 8 for copper, silver, gold, something in that. Well, I don't remember those. I don't use them that often. But I've got a sense of how big they are. So you look at a table of resistivities. I'm pulling up right now, but I'm not going to take time. Okay. So now if I wanted the resistance of an equal length of copper, it's going to be relevant loud because we're going to be dealing with things in nichrome and copper and making circuits out of it and stuff. Okay. If you have the same length of copper, then okay, nichrome is on the order of 1/100th of the resistivity of copper. So it means if you have the same length of copper, you only have 1/100th resistance, which would mean a 1 millimeter cross section of copper, 2 meters long, would have a resistance of 1/10 of an ohm, 100th of that. And it'd be less than that. The resistivities maybe 1/200th of this. It's not that high. not as high as 5 × 10⁻⁸ ohm. All right, so you want to kind of have a sense of that. So when we set up these circuits, you can visualize how much resistance that copper has versus how much resistance that nichrome has. And I've got some nice thin, three thicknesses of thin nichrome. You'll be able to probe down and determine a pretty good approximation with resistivity of nichrome, of that nichrome is. If we had 1/10 of a millimeter square, what would that do to the resistance? Well, if it's 1/10 of a millimeter, it's 100th of the cross-sectional area. That's the thickness, 100th of the cross-sectional area. And a lot of this nichrome has diameters on the order of tenths of a millimeter. It goes up to 38 gauge, which is pretty thin. You break it with your hands. You got a good grip on it, maybe. You wouldn't want to really break it with your hands because you cut your fingers off. Too thin, too much pressure. Okay, so just get another feel. If this is accurate, it's not accurate, it's in the right ballpark. You get 1,000 ohms. You got 1/10 of that diameter, or 1/10 of the cross section. So we should be able to get pretty good resistance out of this stuff. If we don't get good resistance, then we got to get clever. So I'll have a chance to do that too. Okay, well, that's a lot of the content of this chapter. Although when you get into the problem sets, into my lab problems, they have some pretty probing questions. Going back to this I equals V over R. We have these three rearrangements of that same relation. What are the units? Well, your voltage is in joules per coulomb over coulombs per second. And joules is Newton meters, which is actually kilogram meter squared per second squared per coulomb. Times coulombs per second, which is in kilogram meter squared per coulomb second. A lot more convenient to talk about ohms. That's not very intuitive. That's if I broke that down correctly. And I didn't do that right. Thought I was inverting my coulomb per second. I just repeated it. You get coulomb squared. And just a mess. Okay, kilogram meter squared per coulomb squared second. I might have actually written that out correctly. Even though I wrote this out wrong, that's better clearly. Was that right? You got a second denominator, second there, so. You just seconded the denominator. Coulomb squared. Which I've known all along. Okay. Okay, let's say you've got a current. Current. Five amps, voltage, 100 volts. Some power. The power work over time, isn't it? Okay. That's power, 100 volts is 100 joules per coulomb. Five amps is 5 coulombs per second. Now, what will we do with 100 joules per coulomb and 5 coulombs per second? You get power. The powers work over time, right? So the unit should be joules over seconds. So what we'll do if these two quantities get joules over seconds? Well, pretty clearly we multiply them. Joules per coulomb times coulombs per second is joules per second. Now, does that make sense? Oh, yeah. Get 500 joules per second or 500 watts. Does it make sense? Well, yeah. You got 100 volts between here and here, and 5 amps running through it. Okay. Then for every coulomb that goes through here, you get 100 joules. Okay. You got 5 coulombs every second, that's 100 joules every second. So it makes perfect sense if you understand what potential difference means. Think about it in a circuit. Okay, that's real relevant to what we're going to do in a couple of days. Got a battery. A battery has a source of EMF. That's the chemical between the anode, the cathode, and transport of ions and stuff like that. Okay, but we're not going to talk about that. Really, chemistry, all those kind of things. There's a resistance within that battery. In other words, current doesn't go for free through that battery. So here's your battery. And we could put a voltmeter across the battery. I'll explain to you in a minute. for the voltmeter. And now we have some other resistance here. Let's call this R. And call this one R sub B. Called internal resistance. I could use R sub I or R internal or something of that nature. I don't want to use R sub I because you're seeing a lot of sub I's in calculus right now. So we got this, and we got some source of EML. Here. So how much voltage are we getting across this resistor? Well, we're not getting the full voltage that's produced by that cell, because the current is running through the internal resistance of the battery. We do get some current, okay? Inner current is in this direction, goes from positive to negative. This is positive. That one's positive, that one's negative. The current goes this way. We assume that the wires have negligible resistance. They're thick enough and they're good conductors. And they're not too loud. What's the voltage across this resistor? Now, the symbol for voltmeter is just plain old V in a circle. So putting a V sub R in that circle isn't really kosher, but I'm doing it anyway, because I don't want to have to write it separately. Okay. And we'll call this V sub S, voltage of the source. Well, you got a current I going through the resistor. How does the current I get through the resistor? Well, creates an electric field in the resistor. Now, the resistor might be a chunk of semiconductor. Okay. And that's basically what it is. It's a chunk of stuff. You know what resistors look like, don't you? You see? I can show you. I have to find. Okay. It's just a little cylinder with wires coming out the end and some markings on it to tell you what the resistance is supposed to be. Current goes through that resistor. That's got a pretty big cross section. The high resistance resistors are usually much smaller than the low resistance resistors. Does that make sense? Well, yeah, less cross-sectional area means less current for the current density. They got some length. So whatever the voltage is across it, it gives you an electric field. It's that voltage divided by that length. Okay. So bigger cross-sectional area, less resistance, smaller cross-sectional area, greater resistance. Now they can mess with the mix of the material in the resistor, so that the resistivity of that material can differ. So you can have a small resistance and a small resistor. But usually you want the small resistance and a bigger resistor because it's got to dissipate the heat. Current running through resistance, use your power. We just saw that. Where does that power go? That power typically keeps the wire, keeps the resistor. The bigger resistor is going to dissipate heat more easily than a small one. So you make the resistor too small, you'll burn it up. Resistors are weighted, rated. They're weighted. They're rated in watts. Okay. So you may be 0.25 watts. Now that's a lot about resistors. So, but you basically think of that resistor as just a thick wire with very, very low conductivity, high resistivity. So when the current goes through the resistor, well, how does the current get through the resistor? It takes a voltage, doesn't it? So the voltage across that resistor is just the current times the resistance. Up here, you get a voltage across here. Voltage of the source equals current times resistance of the battery. Now, what do we know about voltages? Voltage is the amount of work you do per coulomb. And they got the same number of coulombs go through here as go through here in a given unit of time. So that voltage of the source plus the voltage of the resistor equals the EMF. Which means have this. Voltage of the source, current times the resistance of the battery. I should call that resistance of the source. I better usually ask her if it's going to be handy if we match ourselves. Should have done that in the first place. Anyway, solve for I, you got the EMF divided by resistance of the source plus whatever the resistance of the circuit is. So if you got a 1.5 volt battery, which the batteries standard AC and D batteries and double A. And I've never even seen that. Anyway, you got double A's, triple A's, C's and D's. Those are all 1.5 volt batteries. The bigger ones have less internal resistance. Smaller ones, there's more internal resistance. We'll measure that. So the bigger ones are going to give you more voltage across your load. Across the resistance of the circuit. Let's. It's going to be relevant to things we measure because we're going to use the hand crank generator sometimes, and sometimes we use batteries. Let me explain how a voltmeter works. In order to measure the current across this resistor, we could just take a couple of wires here. This is a coil of wire. Coil of wire is between a couple of magnets. And we've already seen how magnets react with currents. At least we've seen a lot of that. So the coil is going to want to rotate in between the magnets. You have a sensitive meter. That coil is going to have a very strong reaction to even a small magnetic or a small current. Okay, lots of loops of the coil between two powerful magnets. It's going to be so sensitive if we even run a thousandth of an amp, even a millionth of an amp through the coil, it'll ruin the coil. So what we do is, yeah, okay, we have that coil there. But before this gets to the coil, we put a pretty big resistance so that not much current goes through there. And that has two advantages. Number one, it doesn't pull much current from the circuit. It doesn't reduce the current in the circuit very much. My second advantage is it protects that coil, because you don't get much current through the coil. But that's kind of the way a voltmeter works. It just consists of a big resistance and a coil. Doesn't pull much current. Doesn't damage the coil. An ammeter, we're going to measure the current. Draw pudding. Our looking ammeter. I need a little more room. Okay, so but let's just do it like this. Let's say, okay, here we go. Now we're gonna. We're gonna let our current run through the coil, except we better not let our current run through the coil because it's too much current. It'll fill the coil. So what we do is we cut across here with a small resistance. A big resistance and a small resistance. Across this coil, the big resistance prevents a whole lot of current run across the coil. Now, the current into this point here splits into the current through this and the current through the coil. By putting a small resistance here, most of the current goes through here. Now we could talk about the voltage drop and so forth. There's a little voltage drop between here and here. If this resistance is small enough, it isn't much. This resistance is big enough that not much of the current goes through here. And that's your whole idea. Okay, so this is your ammeter. The ammeter has to interrupt the current. What happens if you put this voltmeter in series with the current? So you break the current here and run through this. Well, this is a big resistance. Actually, I circled too much. Here's your voltmeter. This resistance is the resistance of the circuit. resistance across which you're measuring the voltage. If I put this in parallel series with the circuit, then I've introduced this huge resistance and it kills your circuit. In other words, you get very little current if you hook this up in series, because you're putting a big resistance in. If I had a big resistance here and a big resistance here, it would kill the circuit because the current would have to go through the big resistance. Okay. And wouldn't do much. Okay, well, that's the idea. If you were to put this ammeter in parallel across a large resistance, then too much current would go through the ammeter. It'd be bad for the ammeter. Okay, well, we want to keep that in mind. Or what we do in lab. It might not be totally clear why I need this small resistance. Why don't you just put this in there? Well, if you didn't have that small resistance, you'd be blocking the current again. Okay. Why do you have any resistance at all here? Why don't you just put a wire here with no resistance? Well, if you had a wire here with no resistance, you'd have no voltage between this point and this point. If you have no voltage between this point and this point, then you don't drive a current through the coil and you don't get a measurement. You don't get any deflection. So that's basically what it comes down to.